Okay, it's a couple minutes after 2 o'clock. We'll get started here. Again, I'm Jim Benke with Rayco. We have Warren Dean with us from Siemens. Talk about laser gas analyzers. Give Warren a little introduction here, and then we'll get started. We do have everybody on mute. If you do have questions as we get through this, please go ahead and type them in the box, and we will get to them after the presentation. So let's get started. Warren Dean is the Senior Strategic Sales Manager for Lasers and Continuous Gas Analyzers at Siemens Industries. He has a bachelor's degree in chemistry and biology and an MBA from the University of Delaware. He has 38 years experience in sales and marketing with several major process analyzer manufacturers and 19 years with Siemens Laser Products. We welcome Warren as our speaker and thank him for sharing his expertise with our customers. Okay, Warren, you're on.
Thank you, Jim. If you will put the next slide up, I'd appreciate it.
Okay, coming up. Oh, there we go.
Today's agenda, I would like to go over a number of points that deal with measuring oxygen for safety. And the measurement of oxygen in critical applications is specifically for protecting your people and your operations and facilities from explosions due to excess oxygen, and also your people from suffocating due to lack of oxygen. These are very critical applications that anyone in the process industry must be aware of. Specifically, there are a number of applications that we'd like to consider. Number one for safety is thermal oxidizers. You have to make sure the thermal oxidizer is operating correctly, or otherwise it could be an explosion hazard. Number two, flare gas analysis. You have to make sure that the oxygen level in the flare gas is set at a certain level below which an explosion can occur. And then number three is inert blanketing. If the inert blanketing fails, then there's a possibility of explosion. And then also oxygen deficiency. If you have oxygen deficiency, then you can have a case where your operators aren't breathing enough oxygen and they pass out, and we can have hazardous results from that. Okay, once the application has been identified, the critical application has been identified, then the engineer has to look at, what am I going to use? Am I going to use an in-situ or a extractive type sampling technology? The in-situ technology is good because you never have to touch the sample. You never have to alter the sample. This is very critical for components that are reactive because many reactive components will, when they come in contact with the sample handling system, change, and you get a very poor response. In-situ is also good for fast analysis. The in-situ application that we're going to discuss today, TDL, will give you an up to a 3-second response, extremely fast. In-situ also gives you an average across the stack result rather than a point sampling result. If you have a point sampling result, you simply know what is at the point of sampling and not the average across the stack. Also, in-situ requires typically very little calibration. For the application I'm going to discuss today, it's 1 year. You don't have to cal check the unit for a year. And then also, in-situ applications require very low maintenance compared to the extractive type applications. In a typical in-situ application, there's no moving parts. There's no rubbing parts, no grinding parts, no parts to go bad or to wear out. Where an extractive system is a little bit different. You have to pull the sample out of the process. And when you pull the sample out of the process, you can affect the sample. You can change it, and you won't get an accurate measurement. Also, an extractive sampling system is a point sample. You only measure at the point where you're extracting the sample. You're not measuring throughout the entire duct or vessel or stack. Also, extraction monitors require more frequent calibration, at least monthly. And then lastly, an extractive system typically has higher maintenance. There are pumps, filters, coolers, heated lines that have to be maintained versus an in-situ sample handling system. Now, that doesn't say that the extractive sample handling system is always used and the in-situ is always discarded and the in-situ sample is always used. You have to consider the application. In considering the application, what one needs to look at is the speed of response. How fast do you need to have an update on your analysis? If you need a fast response, then the in-situ is the way to go. If you don't care about your time, let's say a 5-minute update is fine or 3-minute update is fine, then an in-situ sampling system and analyzer is fine. Also, we need to consider the interference or the accuracy. The extractive sample handling systems and analyzers don't have the same accuracy as the in-situ does, given the TDL's inherent lack of interference, especially when measuring oxygen. And then lastly, you need to consider the maintenance. How much maintenance can I handle? Is it critical that the instrument is up and running all the time? Can I take it down and maintain it? If you want an uptime that's very high, then use the in-situ TDL. If it's not critical, then the extractive sample handling system will do. So what I'd like to do now is go over how the tunable laser diode works, what its pieces are, and then basically where you would use it and its advantages over other techniques. And then afterwards we'll have a few minutes to answer your questions. Okay, can you transfer it over to me now? All right. Well, I can't pull that out. I'm trying to pull my screen out here. Let's try it another way. I'm not able to pull my screen out from underneath your screen, Rose or Beth.
Okay.
Let's see here.
Warren, if you'd like me to, I'll take it, and
Yeah,
you can just tell me when to advance.
That's perfect. Great, thank you.
Let's see if I can make myself the presenter.
Mm-hmm.
There we go.
I think you have my slides. Yeah. Perfect. Thank you very much.
There we go.
Okay.
You're seeing my screen, yes?
Perfect. Yes, thank you very much. The instrument that I'd like to discuss today and the technique I'd like to discuss for oxygen for safety measurements is the Siemens C-Trans-SL tunable diode laser. And it's designed for oxygen measurements. Next slide, please. As you can see, the instrument, can you see my arrow on the slide?
No.
No. Okay. Well, the instrument is designed in two pieces. It's an all-in-one transmitter like laser where we have a transmitter on one side and a receiver on the other side. And this is mounted at the stack or at the duct or in the process vessel across which the laser is shot. The C-Trans-SL is a non-fiber optic based system. That means that the laser is mounted inside of the launcher and shot across the stack into the detector. There aren't any fiber optic cables used in this case. Next. The C-Trans-SL has a similar sensor and look as our other lasers, the LBS6, which is a fiber optic based unit. Being non-fiber optic, this laser is much more economical, and it also gives us a higher sensitivity, plus or minus 200 parts per million oxygen. And it also requires no central unit. This allows the complete system to be mounted right out the stack. You don't need an analyzer house or shelter as in some other systems. Next. The applications for oxygen for safety is, like I said, safety monitoring, but in addition, process control. If your process control gets out of whack, you're going to have not only issues to deal with safety, but also issues with losing money and not optimizing your process. Combustion control for boilers is another good application. Combustion control for municipal waste incinerators. And also we have a number of applications in steel plants, converters and coke gas analysis. Next. Okay. This will slowly but surely load. All right. You see a transmitter on the left-hand side, and this houses the laser. The laser is shot from the transmitter across the stack to the receiver on the right-hand side. And the receiver takes the laser energy that is shot, transmits it to the display here or down to a control unit. We know how much energy is released from the transmitter. We know how much energy is absorbed by the oxygen, or we know how much energy is received by the detector. The energy lost is the energy absorbed by the oxygen. Next. It'll take a second for it to load. This is a very important slide. As you can see on the left-hand side is a transmitter, and the laser originates from the transmitter. It goes along the transmitter through the process and then comes in contact with a reference cell. This is a built-in reference cell. This reference cell holds an isotope of oxygen, oxygen 18. And this reference cell gives the laser a line lock. It gives the laser a constant absorption of the isotope 18. It tells the laser this is where oxygen 18 is, no matter what. It's always there. So the laser then goes so many wavelengths to the left, and it knows that oxygen 16, what we want to measure, that's exactly where it is. So the laser always knows where the oxygen 16 is because it has an internal reference cell filled with oxygen 18. Well, why is this important? Well, in many of the oxygen applications, the oxygen goes to zero, or it's always zero, and then, or close to zero, and only when it pops up is there real danger. It's a known fact that all lasers drift, and without an oxygen peak on which the laser to lock onto, it'll drift all over the place. All the lasers will. We are the only analyzer, the only oxygen laser that has an internal reference cell using the oxygen 18 isotope. This gives us a line lock so we always know exactly where the oxygen peak is, whether you have oxygen or not. Why is this important? It's important because if the laser drifts off of the oxygen peak and the oxygen peak comes back and the laser can't measure oxygen, you're getting an abnormally low reading and you could be in the danger zone. It's very important to have a line lock for oxygen measurement, and C-Trans SL always has a line lock. Next. The C-Trans SL is suitable for Class 1, Division 1 FM approval, groups A, B, C, and D, without purging, and also we can get it, and this is a Senelec version as well. So you can mount this anywhere, regardless of the area classification, without purge air. Next. Let's take a look at the cost of ownership between an in-situ and extracted type of a system. The instrument costs, let's assume that they're about equal. The installation work, you require 2 flanges for the in-situ, 1 flange for the extractive. You require some cabling. You require pneumatic, meaning air or fan. But the in-situ unit is a field device. You do not require a shelter. The extractive analyzers always require a shelter. Startup, I've seen these units started up in an hour. You don't need any parts. You don't have to calibrate. It's automatically calibrated when it comes from the factory. With the extractive system, it's an extremely long startup. You have to make sure that everything is perfect from the sample point right on back into the unit, and then it has to be calibrated. And it can take days. Utilities for the in-situ instrument air, and it requires very low power. And the extractive system has instrument air, but it requires a lot of power, a lot of juice to run that sample handling system. Consumable parts, there are no consumable parts for the in-situ unit for the laser. And for the extractive system, there are quite a few consumable parts, very expensive over time. You lose pumps, you lose filters, you lose heated lines, you lose solenoid valves. Service for the in-situ, we've had these units installed for over 1.5 years without any service. And extractive system, they have to be monitored on a monthly basis, and typically every 6 months servicing is required. Next. Let's look at a comparison of in-situ continuous gas analyzer technologies between the conventional in-situ and the in-situ with laser. With the IR, UV, Vis, and zirconium oxide, they're very sensitive to dust and or alignment. The tunable laser diode is not sensitive to dust at any appreciable degree. And alignment, it can wiggle within plus or minus 1 degree, which is a big deal. The other ones have to be dead right on. The conventional in-situ has a lot of cross interference. Water is a very big cross interference. CO2, SO2, CO, and of course hydrocarbons. with the in-situ laser, this is a very critical point. There is no cross interference to oxygen. No component interferes with oxygen. That's why the in-situ tunable diode lasers unbeatable for flare gas analysis, because the flare gas tends to vary over time. There's no way you can figure out the cross interferences. So whenever you have cross interference issues, the in-situ laser is the unit of choice. Also, there's a limited lifetime in the light sources in the IR, UV, and VIS, where the laser diode is 6 years plus. I've seen them 12, 14 years. The in-situ conventional units, you have to take them offline to calibrate it. You don't have to take the unit offline to calibrate the laser. It has a built-in self-calibration. And there's also some signal treatment or time for the conventional in-situ to make a measurement where the laser is in real time. When I say real time, it's about 3 seconds. And as always, the conventional in-situ is a probe type or a point-like measurement. You're only measuring at the point of where your probe is. Where the tunable diode laser is a line of sight, it gives an average across the actual duct or vessel or stack. And it eliminates the problem with stratification. Next. We have 3 standard applications. One's called combustion control. The second is safety monitoring, and the third is process control. Basically, they vary with volume, with the actual range. You can go from 0 to 100%, down to 0 to 30%. The optical path lengths are all greater than, well, about 25 feet maximum. And they all have a minimum detectable limit of 200 parts per million oxygen, which is pretty darn good. One of the applications can go as high as 600 degrees centigrade, and the other 2 are about 200 degrees centigrade. And the lower temperature applications can have higher pressure, 5,000 hectopascals. That's about 5 bar. So that's 5 times 15, or whoever can do that in their head. It's a fairly high calculation, fairly high value, versus the higher temperature range of 0 to 600 degrees centigrade. It can give you just barely at atmospheric pressure. So whenever you have higher pressure, you use the safety monitoring and the process control applications. They all can handle a pretty high amount of dust, 10 grams per meter cube, which if you think about it, you take a cubic meter and put 10 grams of dust in it. That's quite a bit. And they take about typically 10 seconds, some lower, to integrate. And they all use purge gas, nitrogen. Next. In summary, if you're using a TDL for an oxygen critical application, the key point to remember is that it has an internal reference cell of the isotope 18. This is a non-interfering gas, and it allows the analyzer to remain stable, and it allows it to have a line lock on oxygen regardless of whether the oxygen in the process goes down to 0 or not. Secondly, you can put the analyzer in a Class 1, Div 1, Group A, FM approved area without any purge gas. Thirdly, you don't need to have any type of wires connection to the unit to talk to it. It has a keypad that operates via infrared signal that you can program the unit directly. Profibus is available as a communication. And also, the tunable diode laser for oxygen safety has a very good cost ratio because the instrument is very low maintenance. It has no moving parts. It's easy to align. It's easy to take care of. And services, like I said, I've seen these go for 1.5 years, 2 years before requiring any service. So all in all, it's a very efficient and very accurate type of technology for safety oxygen measurement. Next. Thank you very much, and I'll take any questions that you have.
Okay, Warren, we do have a couple of questions that have come in.
Okay.
First one here is, I have a dusty process. How do you keep the lens from getting dirty?
Okay, that's a very good question. On either side of the laser, on the transmitter and the receiver side, there's an inlet for purge gas. And you apply purge gas to these inlets, and they put a small pillow of air in front of, or nitrogen in effect for oxygen. They put a small pillow of nitrogen in front of the lens, whereby the process dust cannot get on it.
Okay. Good. Here's another one. What's the max temperature the unit can handle?
The temperature can, the temperature of the process is 600 degrees centigrade. That's the maximum temperature. That's high enough for most applications.
Okay. Here's another one. What happens if the gas composition changes?
Oh, that's another good question. The tunable diode laser design is such that there is no component in the universe that absorbs in the area that oxygen absorbs. So there is no interference whatsoever, regardless of the background gas changes. That's a very good question.
Okay. Okay, looking for a couple more. Oh, here's another one. How do you know the unit works if you don't calibrate it for a year?
Well, the unit always has an internal reference cell, and it always is monitoring that internal reference cell to make sure that it can see the oxygen 18 peak. And if it can't see it, then it's not working, and you'll get an alarm that says, hey, I'm not working. That, too, is a very clever question. If you don't have an internal reference cell, then you really don't know if your TDL analyzer is working. That's why you always need an internal reference cell when purchasing a tunable diode laser.
Okay. That looks like it for the questions that have been coming in. So I think we're good with our question and answer portion of this quick webinar. I would just like to let everybody know that we are recording this webinar, and it will be available, including the slides, over on the RACO website. Just go over to the RACO Training Center. It'll probably get on there early next week, and you'll be able to view it again on your own. Okay. Oh, okay. We've also got staying in touch with RACO as well too. We've got a couple of different areas that people can get in on. We've got a blog, LinkedIn, Twitter, and also YouTube. Please make sure that you check those for updates. Warren, we'd like to thank you very much for your time today. We do very much appreciate it. RACO continues to offer webinars. In fact, we do have another webinar scheduled for Thursday, September 15th, where we're going to have Werner Haag from Ion Science going over the PID analyzers that Ion Science has to offer. So I did not see any more questions come in. We're right up half an hour of webinar. I'd like to thank everybody for joining us, and please check the website for updates and a copy of this webinar. Thanks again for attending.
Thank you.